Time to practice again. So now we have the decomposition of KClO3 is commonly used to prepare small amounts of oxygen in the laboratory. How many grams of O2 can be prepared from 4.5 grams of KClO3? Well, let's see. What would be our first step? We probably would need a balanced equation. So let's write that first. So we have KClO3 is decomposed, so that means we're going to break it down, and we're going to get oxygen apparently. And what else do you think we could get? Well, what's left if we take away the oxygen from the KClO3? Yep, you guessed it, that'd be KCl. Okay, now what do we need to do? Well, now we need to balance the thing, yes? So remember that we're going to do metals first, and then nonmetals, and then oxygen finally, because oxygen is always the problem. As it is here as well. Potassium, 1 on each side, chlorine, 1 on each side, those are good. Now we've got 3 oxygens on the left, and 2 oxygens on the right. So in order to balance these, we're going to have to find the least common multiple, which happens to be 6. So in order to get 6 oxygens on the left, I would multiply the whole thing by 2. And over here I'd need to multiply by 3. And then now I've changed to 2 potassiums and 2 chlorines apiece, so I need to make this a 2. Hopefully you all remember how to balance equations, and that was not terribly difficult. Now, we're going to take what we start with, the 4.50 grams of KClO3, and we need to convert that to grams of oxygen. So remember your stoichiometry map from last year, if you're using that. The first step would be to convert grams to moles, and we're going to use the atomic mass of KClO3, which happens to be 122.6 grams. And we're going to convert to 1 mole, because remember, by definition, the molar mass is 1 mole of any substance. Then the next step is the most important in any stoichiometry problem, where you have your ratio. And you're always going to have the ratio of what you're interested in, or the thing that you want is going to go in the top. The thing that you have is going to go in the bottom. All right, and finally we need to convert back to grams of oxygen, so we're going to multiply by 16, everybody? No, Mrs. Kovach, it's 32 because oxygen is diatomic. Okay, and if we do our math, we should come up with 1.76 grams of oxygen. Now, just a word about significant figures. Is that the correct number? Yes, it is, because how many did we start with? Well, here we have 3 significant figures, and so our answer should have 3 significant figures. Good job. And now on to the concept of limiting reactants. Remember that the reactant that is completely consumed in a reaction is called either the limiting reactant or the limiting reagent sometimes. The other reactants that are present are sometimes referred to as in excess, because there's more of them than what you really would need, so they're in excess. Alrighty, so now we're going to do a problem. A mixture of 1.5 moles of aluminum and 3 moles of chlorine is allowed to react. What's the limiting reactant? Well, in order to answer that question, we're going to have to balance the equation, right? So let me give you a minute to do that, or pause the video here, write and balance your equation, and then I'll give you the correct balanced equation. Go. Okay, we're back. So the correctly balanced equation is going to be aluminum plus chlorine is going to give us aluminum chloride. I hope you got the right formula there, AlCl3. And if we balance this, we need a 2 here, and a 3 here, and a 2 there. So now we have that balanced. All right, so now we need to figure out if we have 1.5 moles of aluminum, how much chlorine do we actually need for that amount of aluminum? So for every 2 moles of aluminum, I need 3 moles of chlorine. Now that math would give me, what do you suppose? Well, if we do the math, we get 2.25 moles of chlorine. Now how much chlorine do we actually have? Well, we have 3 moles of chlorine, so the chlorine is probably in excess here. So that means, but we should probably do the other part of this. So if we have 3 moles of chlorine, then for every 3 moles of chlorine from the balanced equation there, we need 2 moles of aluminum. So that tells us that we need 2 moles of aluminum for that amount of chlorine. So how much aluminum do we have? Well, we only have 1.5 moles. So that means that the aluminum here is the limiting reactant, right? So that's question A. All right, now question B. How many moles of aluminum chloride can be formed from your the moles of aluminum that you have? So we have 1.50 moles of aluminum multiplied by the molar ratio, and here we're going to say, oh, well, that's 2 moles of aluminum, and we're going to make 2 moles of aluminum chloride, so we can then get 1.5 moles of aluminum chloride. Right, and finally, we have question C, which says, how many moles of the excess reactant remain? Well, remember back in part A, let me use my pointer here. Back in part A, we determined that we have 2.25 moles of chlorine necessary to react with 1.5 moles of aluminum. And we know that we have, up here, 3 moles of chlorine. So that would mean that in order to figure out the excess, we would take the 3 moles that we have minus the 2.25 moles that were required, and that would give us 0.75 moles chlorine in excess. Good job. Last topic for chapter 3, or for stoichiometry, is theoretical, actual, and percent yields. And these are, of course, 3 things that we did look at last year in honors chemistry. The quantity of product that is calculated to form when all of your limiting reactant reacts is called the theoretical yield. So we're going to associate calculated with theoretical, right? The amount of product that's actually obtained is the actual yield. And then, of course, the percent yield is the actual divided by the theoretical times 100. So those are your 3 definitions. Time to practice. So here's our balanced equation. Fe2O3 plus 3CO yields 2Fe plus 3CO2. We're going to start with 150 grams of Fe2O3, and we're going to convert that to grams of iron. And they're telling us that Fe2O3 is the limiting reactant, so we don't have to worry about calculating that part. So we're going to change grams to moles by dividing by the molar mass of Fe2O3. And then we're going to multiply by the molar ratio. Remember to put the desired substance in the top and the one that you started off with in the bottom. And then finally multiply by the molar mass of the iron as your desired amount. So if we calculate this, we'll get 0.9 grams. And let's round that to 3 significant figures because we can. And now we're going to figure out the percent yield. So remember that the percent yield is calculated by taking the actual yield, which they gave us, divided by the theoretical yield, which we just found. Remember that the theoretical yield is the calculated one, times 100, since it is a percent, and that would give us 83.7%. So here you have it. Congratulations, everybody. We've finished the video on stoichiometry. See you next time.